Imagine if you had a ball and you decided to swing it around in a circle like this. And the velocity of this ball as it travels around in this circular path doesn't change. Let's say it's whatever, 5 meters per second. The magnitude of the velocity is unchanging. However, the object is technically always accelerating. How? That sounds weird, right? When you have an object moving in a circular path like this, the direction is always changing continuously at every moment. And according to Newton's first law, a change in direction counts as acceleration. So even if the magnitude of the velocity is the same, it's always moving at this same speed, the direction is changing. So technically this object is always accelerating. Now imagine you have an object like this and it's traveling in this circular path. After a certain amount of time, it moves here. The vectors look like this, and they're always tangential to the circle curve in this kind of circular motion. Now, the formula for centripetal acceleration, there's a bunch of math behind it, just like there is with every other formula. I'm not going to go through it, but if you did go through it, you would end up subtracting these two vectors. And when you subtract these two vectors graphically, they look like this. This blue vector is the result. This blue vector here is very special because it's always pointing toward the center, always. That is centripetal acceleration. The reason why it moves in a circle is because it's always accelerating toward the center. The formula for centripetal acceleration, by the way, I'll spell out centripetal right here. The formula, we'll label it as AC. It's equal to velocity squared divided by radius. Radius is, as you know, the length here. Now here's something that you should keep in mind as you solve circular motion problems. It makes it much more intuitive. The more velocity your object has, so the faster it's going, the more centripetal acceleration. So the faster it changes direction. The larger the radius, so this, the less centripetal acceleration your object will have. In uniform circular motion, so when the velocity is constant throughout, the acceleration, the centripetal acceleration, is always perpendicular to the velocity, as you can see here. So it's always looking something like this as you fly around the circle. Let me teach you about time and frequency for circular motion. Now, if you study trig waves like sine and cosine, this might remind you of that. The formula for time is t equals 1 over f. F is frequency. So, for example, the frequency of your objects is 4 revolutions per second. So it spins around 4 times every second. Then your time would be equal to 1 over 4, which is 0.25 seconds. The formula for velocity is this, which I'll give you here. Now, as you know, velocity is distance over time, which means that we can substitute in our values. The distance is 2 pi r, because that is the circumference of a circle. The time, as we know, is t. Let's run this through an example, and if you want all those formulas in one place, there's a free cheat sheet I made for myself, which I'm sharing with you. You can get it for free in the description. Let's say you have a ball, and your ball is 300 grams. You've attached it to the end of a rope, which is 2 meters long. You decided to start swinging it in a circle for whatever reason, and it makes 2 revolutions per second. What is the centripetal acceleration? Which is this, remember? Well, let's use our new formulas. We're looking for the centripetal acceleration. So the centripetal acceleration is given by velocity squared over radius. But we don't have velocity. Velocity is circumference over time, but we don't have time. So time is 1 over f. Well, now we're ready to solve. We have the frequency. The frequency is 2 because it spins twice per second. That means time is equal to 1 seconds. And velocity is 2 pi times 2 meters, the radius, divided by our new time value, so 0.5. Chuck this into a calculator, you get roughly 25.132 meters per second. Now let's use the centripetal acceleration formula. which is velocity squared, so this number squared, divided by radius, which is 2. And when you solve that, you get roughly 315 meters per second squared. That's the centripetal acceleration of our ball. Here's an example that I'll let you do yourself. So imagine you're designing a delivery drone, you're a drone engineer, and your drone, which we'll label with this circle, it's delivering a payload of 2 kilos. It's a 2 kilo item. But when you deploy your drone, it's very windy and the turbulence means it starts swinging in a circle. It swings at 2 revs per second, so 2 revolutions per second. And the cable of the drone is 1.8 meters to the edge, like that. What is the centripetal acceleration? Go ahead, pause the video, try and find it. Now I'm going to solve it together with you. First, let's find the period, so how long it takes to travel in one circle. That would be t is 1 over f, which is 1 over 2. 2 revolutions. Now let's find the velocity, which is 2 pi r over time. This is 2 pi times 1.8 meters, the radius, divided by time, so 0.5 seconds, which we just solved for here. Now for centripetal acceleration, which is velocity squared over radius. This is about 22.6 squared, which is our answer from here, our velocity, divided by 1.8. And when you run this calculation, you get roughly 284 meters per second squared. That is the centripetal acceleration of this little thing here. Here's a fun one. Let's find the centripetal acceleration of the moon. So this falls under orbital mechanics, which is a really cool sounding topic. Say this is Earth, and you have the path of the moon. Now the moon here is about roughly 384,000 kilometers above Earth. The period, so how long one orbit takes, period is t, which is 27.3 days roughly. From this, are you able to find the centripetal acceleration? Let's solve this together. Now, when it comes to centripetal acceleration and you look at the formula, what do you need? What are we missing? Well, we have radius. We just need velocity. We don't even need to solve for time because we don't have that here. Let's go ahead and plug in our values. So as you know, velocity is circumference, so this divided by time, which is this. Let's quickly convert days to seconds. There, that's our answers in seconds. So it takes this many seconds for the moon to travel around the Earth. Next, we have to convert this to meters, which is very simple. We just times 1,000, which means we just add 3 zeros. That's equal to 3.84 times 10 to the power 6 in scientific notation. Let's plug in our values and find velocity. So this would be this here and this here. These are some big numbers. I'm not going to write it all out, but just know that your tangential velocity is equal to 1020 meters per second. Now we're ready to find centripetal acceleration. Formula is AC is v squared over r. Put in this for v and put in this value for radius. When you plug in your values, you'll get roughly 0.00272 meters per second squared, which is in scientific notation 2.72 times 10 to the power 3 meters per second squared. Now this is a very small number, and you might be surprised because the moon, as you know, is moving very fast throughout space. The reason why this number is so small, even though the moon is so fast, because the centripetal acceleration of an object gets lower when the radius is bigger, which is what I was talking about earlier. See the radius? The moon is very far. Now that was the kinematics of circular motion. It was acceleration and velocity. But how about the dynamics of circular motion? So now we're going to count forces. When you have an object moving in a circle, we know that it's always accelerating. Newton's second law says that for an object to be accelerating, there has to be a net force acting on it in some way. So that means in circular movement, there's always a constant force being applied to keep it moving. Now, what is this net force? The magnitude of this net force, well, when we apply the second law in the radial direction basically just means the centripetal direction toward the center. Now look here, this here AC, that's centripetal acceleration. So here's a very important formula. This is the formula for centripetal force. Fc for centripetal is equal to mass times velocity squared over radius. And we took this from the formula for centripetal acceleration. This formula is also on the free cheat sheet, and we're going to be using it quite a lot. Now here's something interesting about centripetal force. There must always be another object applying the force. For example, when you're swinging a ball, you're pulling on the rope. Or when the moon spins around the earth, gravity is pulling it in. So centripetal force and circular motion doesn't come out of nowhere. And let's use the same diagram to explain a misconception. If you've ever swung something in a circle, like, the classic ball on a string example, you might feel a force pulling it out. You might feel something pulling it away, That would be centrifugal. But here's the thing. There is actually no force pulling it out. Even in this example of you pulling a ball on a string, when you pull on the string, the ball exerts a force back. That's what you're feeling. Because third law, every action has its equal and opposite reaction. If you want proof of this, and here's real life proof. When you swing a ball in a circle like this, and you swing it really, really fast, and you let go, what happens to the ball? It doesn't start flying off like that, because there's no outward force. It flies off instead like that. Here's a fun example to make use of the concepts we just learned. Let's say you're at a famous theme park and they have a very special ride. It's a super fast spinning roller coaster arm thing. And you sit on the end of it. Let's draw a diagram. Right. Here's the arm. And you sit here at the edge. Which we'll draw a circle for that. And it's a very, very fast spinning ride. It's spinning horizontally. Let's say that the mass of this thing at the end is 3.2 kilos. The radius is 0.8 meters, and it spins twice per second. What is the centripetal force acting on you? Let's draw the forces acting on an object. First one, we have gravity. And here's the force providing the centripetal acceleration. It is the mechanical arm that spins around, which is the tension. Let's find what we're missing. So the formula, if you remember, for centripetal force is Fc equals mv squared over r. We know the mass is 3.2 kilos. We know the radius is 0.8 meters. What are we missing? We need velocity squared. When you solve for velocity with the formula, so 2 pi times 0.8 meters, the radius, divided by 0.5 seconds, which is the period, you get somewhere around 10.05 meters per second. Plug this into the formula, you get Fc equals 3.2 kilos times 10 meters per second divided by 0.8 meters, the radius. This gives you 404 newtons of force. So the centripetal force is 404 newtons. When you're spinning around really fast, you're getting pulled toward the center with this many newtons. Now there's a second approach you could have taken. This centripetal force formula, right, mv squared over r, you can write it as m times centripetal acceleration. It's the same thing. So if you wanted to find centripetal acceleration separately, like this, then plug it in, that would give you the same answer. So it's just up to preference which formula you would like to remember. Now how about gravity? We didn't consider gravity here. In this example, gravity, if you went and solved it, would be only a few newtons. It would have a negligible effect on things like the force here and how fast it's moving. So we're not going to consider it in this problem because it's just not worth it. So we've done a lot of examples on horizontal movement. So swing a ball around you or the roller coaster. What about vertical movement? So let's draw a proper diagram for this. This problem is a lot of fun, and I think you might be able to relate to it. Imagine a child playing at the beach, and he fills a bucket up with water. And his bucket, let's draw it like this, he begins swinging it around in a circle, like this. Let's assume this motion is non-uniform, which means that at some points it will be faster, and at some points it will be slower. It's not constant. The child's arm, let's assume he's quite lanky. He has 2.3 meters long arm. And the bucket is filled with 750 grams of water. At this top point, at the peak of the path, how fast does he need to be swinging the bucket to keep the water in the bucket? So basically, to keep it moving. First, with free body diagram problems, we should label the forces. So we have gravity, and we have the tension of the handle, which is same here. We have gravity and the tension of the handle. Now the tension of the handle is the centripetal force. And the question is asking us, what's the minimum speed? The minimum speed would be when tension is equal to 0. Why? Well, we have two forces acting on our bucket, right? Gravity and tension. At the top, the minimum speed is when tension is 0 because we are relying on gravity to provide enough centripetal acceleration to keep our bucket moving. I'll make this more clear. The minimum speed needed to keep the bucket moving and to keep the water inside the bucket is when we're going fast enough where the force of gravity is providing enough centripetal force to keep it moving. Let me try and visualize for you what's happening at this moment in time. If the bucket is too slow, the water will spill out. And at this moment, the only force acting on it would be gravity. So if gravity is enough, the bucket will barely make it over, and any slower, it will fall straight down, and water will spill on the child's head. That's the minimum speed we need, just to barely push it over with only gravity. So let's find the net force in the radial direction, so toward the center. Right here, we have the net force as gravity. We're not considering tension because remember, tension is 0. Gravity is the centripetal force, and the centripetal force formula is mv²/r. This equation means that gravity is equal to the centripetal force, which means that gravity is keeping us spinning. We can cancel out mass for g equals v²/r. We're looking for the minimum speed at the top, so let's solve for velocity. When you solve for velocity and you rearrange the equation, you get v equals root gr, which is equal to the root of 9.8 times 2.3. Remember, 2.3 is the radius. Then you get roughly 4.75 meters per second. That's the minimum speed your bucket needs to be traveling at for it to not spill water at the top. Now let's ask a second question to expand on this and keep learning. Now take this position at the bottom of the path. If we assume that swinging the bucket down here is twice as fast as the velocity at the top, then what is the tension of the handle? Okay, well first, let's find how fast it's going. We know it's 2 times faster than at the top. And at the top, as we just solved, is 4.75 meters per second. That means velocity at the bottom, which we'll label with b, is 9.5 meters per second. Okay, that's useful. Now we can find the force of tension. Let's consider the net forces acting on this and apply Newton's second law. So F equals ma. The net forces acting on the bucket at the bottom is the tension pulling it up and gravity pulling it down. So subtraction. Now these forces, that is the centripetal force of the bucket. So we can write mv squared over r. I'm going to go ahead and solve this for tension now. There we go, there's our answer. So here's a little tip when it comes to solving physics problems in general. Break it down into parts. You don't have to solve it all at once. Anyway, here's our answer. So at the bottom, the tension of the handle is this, 36.8 newtons. Hello. So this is going to be a quick video because it's not introducing any new physics. It's simply a real-life application of centripetal force and circular motion. So if you imagine a curve on a racetrack, and this is your car, and you're going this way around the track. The centripetal force keeping you on this path is this way, right? Toward the center. And the force is friction. That's the only force pulling you that way. Friction between your tires and the road. So if you imagine your car, here's your car. The force is acting on your car as you turn this corner. Friction going this way. You have gravity going this way. And you have the normal force counteracting going up. But if you've ever gone to a proper racetrack, you might have seen that a lot of the turns are banked, which means they're on an angle, right? They kind of go up like that. Why do they do this? Well, it's actually for a reason, and it's interesting. So take a banked angle. And here, that. The car that drives on this angle, so let's draw it really quick. This car is safer than this car. This is why. So we still have the same forces. We got gravity, friction from the tires pulling it toward the center. But here's the difference. The normal force is always perpendicular to the surface your object is on. So the normal force is actually going this way. And that means the horizontal component of the normal force is helping the friction. It's contributing to the centripetal force, which means that there's less reliance on friction. What's interesting is that at a certain angle, if you get the angle right, the normal force will provide enough centripetal acceleration, centripetal force, to keep your car in a circular motion. So absolutely zero skidding on even very slippery surfaces like icy roads. This concept is used in racetracks, roller coasters especially. That's why you always go sideways and things. And airplane turns. So that's why the airplane, this is the wings, that's why you see it turn like that. Banking. Now if the horizontal component of the normal force is given by Fn, sine of the angle, and this normal force is enough to keep your object in circular motion. It is all you need when it comes to centripetal force. That means it's equal to mv squared over r. So you'll recognize this formula as the centripetal force formula. Anyways, I'm not going to go through any examples. I just thought this was a fun idea. And you might see this on your test. So if you want extra practice, go check the description. This is a video on non-uniform circular motion. So non-uniform circular motion means that when you have an object swinging around in a circle, at some points it might be faster and at some points it might be slower. It's not moving at a constant speed. Why might an object not move in uniform motion? Well, as you know, at uniform motion, a net force in the radial direction is constantly being applied. But what if this net force was at an angle like that instead of straight toward the center? Now you'll see examples of this in real life. For example, those Olympic shot put throwers, and they spin faster and faster and faster. So the object in their hand goes faster and faster and faster. It's not at a uniform speed, it's accelerating. Now the components of this force can be broken down like this. You got this component and this component. This is the tangential acceleration. So we'll label this with A, T. This right here is pointing toward the center. So that would be AC, right? Centripetal acceleration, which we are familiar with. That means the tangential acceleration is always parallel to the velocity. But that doesn't mean it's always in the same direction. Because if your object is slowing down, your acceleration is going to be backwards. It's still parallel, but an opposite direction. Now, because of how vector math and Pythagoras works, we can find this vector magnitude with this formula. So we'll label this as A is equal to AT plus AC as vectors. So since it's vectors and they work differently to normal arithmetic, the formula is Pythagoras. AT squared plus AC squared. That's the conceptual idea behind non-uniform circular motion. Let's do an example. So imagine you have a launch pad for a drone. Your drone sits on top like this. It accelerates at a uniform rate in a circular path. And it accelerates until it reaches a speed of 25 meters per second. It takes 7 seconds to do this, and the radius of its path is 500 meters. Let's find the tangential acceleration. Now here I'm going to introduce you the formula for tangential acceleration, which is AT equals delta V over delta T. This may look familiar. This is from the very beginning of physics. Simple acceleration formula. So that means if our drone is here and it's accelerating like this, we can find this component, the tangential acceleration, with this formula. The change in velocity is 25 meters per second and the change in time is 7 seconds. This gives us roughly 3.57 meters per second squared. Okay, great. Cool. That is the tangential acceleration of our drone. What if we wanted to find the centripetal acceleration when velocity is equal to 10 meters per second? So at the peak, it's 25 meters per second. But somewhere along the way, it's going to reach 10 meters per second. The centripetal acceleration at this point, we can just use the simple centripetal acceleration formula. It's AC equals velocity squared over r. Velocity squared is 10 times 10, so 100 meters per second, and the radius is 500. This is equal to 0.2 meters per second squared. That's how fast it's accelerating toward the center, which is one of the components of this angular vector. By the way, here's a note. This tangential acceleration, it remains constant. It's constantly accelerating at the same speed. But what changes is the centripetal acceleration, which increases throughout. And this is because of a concept of the more velocity, the more centripetal acceleration. So since the tangential velocity is rising, then so is the centripetal acceleration. But it's rising at a constant rate. So tangential acceleration is uniform. There's a famous story where Isaac Newton was sitting under a tree and an apple fell down. And when this apple fell, he saw it and he asked the greatest question ever asked by humans. If the apple falls from the tree, why does the moon in the sky not fall either? And this led to him developing Newton's law of universal gravitation, which I hope you understand right now. Imagine if you and the earth that you're standing on, is connected by an invisible rope. This rope pulls you toward Earth and pulls Earth toward you. This invisible rope is called gravity. Now imagine that every particle in the universe, every star, every planet, every moon, every animal, every particle, everything is connected by these ropes. That is Newton's law of universal gravitation. that everything is acting on each other with gravity. Everything is pulling toward each other in some way, no matter how minuscule. So his law in equation form is F equals G m1 m2 over r squared. Let's break this down. This G is called the universal gravitational constant, and it's a super precise, super important number, because if it was too small, everything would fall apart, we wouldn't exist. If it was too big, everything would implode. This means the force of gravity, so let's write this out. M1 and M2 just means the mass of the two objects, and the radius is the distance between them. By the way, here's the accepted value for the gravitational constant. Now, of course, you don't have to memorize this or anything, and it's some cool science. Let's go through a fun example. Do two dogs attract each other gravitationally? Let's have dog 1, let's draw him, so doggy. And dog 1 is 10 kilos. Dog number 2, so his new friend that he met at the park, he's not very happy, he's sad. And dog 2 is 20 kilos, he's quite a bit fatter. They are sitting 0.5 meters apart from each other. How strong are they attracting each other gravitationally? Let's check with Newton's law of gravitation. Now here's something interesting. This is called forces acting at a distance, because before Newton came up with this idea, we thought forces were all exerted by some other force, like you pulling open your door or you lifting up an object. People had some trouble accepting the idea of two objects acting on each other with forces without touching. So forces at a distance like gravity are called non-contact forces. Anyway, moving on with the solving, we just have to substitute everything in. I'm going to speed it up because it's some big numbers. This is roughly 5.04 times 10 to the negative 8 newtons. This number is so small that it's unnoticeable. You cannot notice these two dogs attracting each other. And even if you did care about this tiny force, usually the force like friction and tension in muscles is way stronger. So this gravitational attraction between these two doggies is impossible to see. Here's a cool space example. This is Earth, alright? And this is the radius of Earth. Let's say you have a satellite and it's 2 radii away, which means that your satellite is twice the radius of Earth away in distance. So if this is radius of Earth, then this is 2 times radius of Earth. Your satellite is spinning around in orbit and it weighs 4,600 kilos. To find how strong gravity is acting on each other here, we could use the law. But let me introduce you a concept called the inverse square law. So as we know, the law of gravitation says this: mass 1, mass 2 times g divided by radius squared. This means that as you get further and further away from Earth or any object, the gravitational force you experience decreases by the square of your distance. Now the force of gravity at the surface of Earth is mg, that's our weight. And our satellite is twice as far, which means that because of the inverse square law, it would be 1 over 2 squared times mg, which is 1 over 4 mg. That means the satellite experiences a quarter of the weight that we experience on the surface of Earth. If you went through and did this calculation, you get 11270 newtons. That's the amount of force gravity is pulling on it. This is a video on how satellites and zero gravity weightlessness. Now let me explain to you something. When you have a satellite in orbit like this, they need enough speed to stay in orbit. If they don't have enough speed, they'll crash to the floor. But at these insanely high speeds, how come they don't just fly off into space? The thing keeping them from doing this is the gravity of Earth, right? So that means they're always getting pulled in the centripetal direction by gravity, which means that they're always falling. That's what being in orbit is. It means always falling toward Earth, but the tangential speed of the satellite keeps it from hitting Earth. Now, the formula for the speed you need to stay in orbit as a satellite is V equals the gravitational constant times the mass of Earth divided by radius, and this is also under the square root. Here's something interesting. This formula doesn't involve the mass of the satellite, only the mass of Earth. So that means no matter how heavy your satellite is, it will move at the same velocity as any other satellite, no matter how heavy. So let's go through a fun problem. You are a scientist from the future, and your task is to build an advanced space station. And they say it needs to hover above the same spot on the equator. So let's say this is Earth. This is the equator of Earth. Your satellite has to hover above the same spot on Earth the whole time. And this is a crucial concept in satellite mechanics. The orbital period of the satellite has to match the rotation of the Earth. Now here's the questions I'll give you. What altitude does your satellite need to stay at in order to remain in sync? The second question, what's the orbital speed required to stay in sync? And the last question, compare the speed to a low orbit satellite that is 200 kilometers above the Earth's surface. I'll put this aside so that we have some space to solve. Let's start with altitude. Now here's what we know. We know the mass of Earth because we can Google that. We know the radius of Earth because we can Google that. And we know the gravitational constant. I'll write it out, but I'll speed it up because they're big numbers. We also know the orbital period. The orbital period of our satellite is 24 hours, which is 86,400 seconds. Now, since our satellite is undergoing circular motion, the gravity is providing all of the centripetal force, which means that the force of gravity is equal to the centripetal force. As we know from Newton's law of gravitation, the force of gravity is equal to G times N1 times M2 divided by radius squared. And centripetal force is given by the formula mv squared over radius. Let's say mass 1 is the mass of the Earth. That means this would be the mass of the satellite. We can cancel these out. And because we know velocity is equal to circumference divided by time, then we end up with this formula. 2 pi r divided by t squared divided by radius. If you're feeling a little lost and you're saying things like, how do you know how to do this? How do you know which things to cancel, which things to solve? Well, I've said this before, but it really just comes with time and experience. When you solve a lot more physics problems, you'll develop a strong intuition for what you should do next. Here, I'll try and explain the logic. We're trying to find a formula for the radius, because the radius is this distance, the altitude. Now, if you want extra practice, go check the description. Let's solve for radius, which gives us radius cubed equals a bunch of stuff here divided by a bunch of stuff like this. That's our formula. We have all the values. We have this, we have this, we have the time, and then all we would have to do is plug. Now, I'm not going to go ahead and plug for the answers because there's a bajillion numbers here, but we do have everything we needed to do if we wanted the radius. Now let's find the orbital speed required for our satellite to stay up, but not just up, but also in sync with Earth's rotation. I explained to you a formula from the start of the video, which is V equals G times the mass of Earth divided by radius. This is the formula for orbital speed. When you plug in our values with a calculator, you get roughly 3,071 meters per second. That's how fast our satellite is moving. And if you went and Googled it, then you would see around 3 kilometers per second. So yeah, our answer is right. That's the orbital speed done. Let's compare the speed of our satellite to a low Earth orbit satellite. So remember this formula, right? For orbital speed. To find the speed of our low Earth orbit satellite, we also need the radius. Let's draw our satellite really quick. Let's say it follows this path, lower. The distance from here to the center of Earth is his orbital radius. That means we can add the radius of Earth with 200,000 meters, which is how high he is above the surface, which is something like 6,571,000 meters. When you plug this into this formula, you plug in the gravitational constant and the mass of Earth, you end up with roughly 7.8 kilometers per second. Now, what was our main satellite speed? It was 3 kilometers per second, right? That's half the speed of the low Earth orbit satellite. This is proof of a concept I think I explained in another video, which is when it comes to centripetal force and centripetal acceleration, the bigger the radius, the slower your thing will go, because centripetal acceleration is smaller. So the further away you are from Earth, the slower you will travel in orbit. Let me teach you about weightlessness now. So when you see people in the ISS, the International Space Station, you think they have zero weight, zero gravity. They're weightless. However, being weightless is not the same as an absence of gravity. People on the ISS actually experience about 90% of the Earth's gravitational pull. On the surface of Earth, down here, the weight you feel, when you feel weight, it's actually the normal force. That's because the floor is pushing the normal force on you. On the ISS, as it flies through space in orbit of Earth, everything is falling at the same speed. So nothing gets the chance to push on you because everything's falling together. That's why you can float around, because you're in free fall technically. Now, why do you feel weightless? Let me try and give you another example. When you go on an elevator and the elevator goes down, the normal force pushing back on you gets weaker as you accelerate down. And I went through this in another video as well. But that's basically what's happening on the ISS. Because you're always falling, you're always accelerating down, you're kind of weightless in a way. About half a century before Newton developed his great theory of motion, a German astronomer called Johannes Kepler, I'm kidding, I don't know how to say his name, Johann probably. Johannes Kepler developed a very detailed description of how the planets fly around the sun. And how he did this was very impressive. He didn't have a telescope. He tracked the stars in the sky with data, and he used math. From his observations over years and years, he developed his laws of planetary motion. The first law is that planets move in ellipses, or ellipses. Basically, they don't orbit in perfect circles. They orbit in more like ovals. The third law is that planets orbiting the sun will speed up when they're closer and slow down when they're further. The third law is that the orbital period, so how long it takes for you to orbit the sun, depends on how far you are from the sun. So like Pluto takes way longer than Earth, because Earth is closer to the sun. This means that the time it takes to orbit the sun is related to your distance in a very predictable way. Mathematically, the third law is this. The ratio between the orbital times of the two planets squared is equal to the ratio of the two distances from the sun cubed. And a variation of it is s cubed divided by time squared 1 is equal to s cubed 2 of the second time squared. Let me give you an example. Let's find Jupiter. So if you Google it, Jupiter orbit is 11.86 Earth years. Let's find its distance from the Sun with Earth as a reference. So the time of Jupiter divided by the time of Earth squared is equal to the distance from the Sun, so the orbital radius of Jupiter, divided by the orbital radius of Earth cubed. You get this as 11.86 squared equals the orbital radius of Jupiter cubed. Now we're going to learn a new unit of measurement. This solves as the distance of Jupiter from the Sun is equal to 5.2 AU. AU means astronomical units. So that means Jupiter from the Sun is 5.2 times further than Earth is from the Sun.